I guess I should start with kind of the basics for people, right? In case they're not familiar with it. But like we're talking about the Mega Drive, and so this is like Mach Effect, right? I mean, is there kind of a layperson's description for that? Or David, you might have that too. I mean,
well, the Mach Effect in general is first, I guess, this idea that gravity relates, there's like interconnected of all the masses, and so, I mean, you could do a better job explaining it, but basically, when you push on a mass, the idea is the masses of all the other universe is pushing back on it, and so there's some inertial effect that Jim is after in relation to Mach's effect. I mean, I'm not necessarily an expert into the Mach effect. It can get a little confusing because Mach's principle is this term that Einstein coined, but then it seems like what Einstein meant by it wasn't exactly what Mach thought either. So then it turns into this can of worms of what is Mach's principle? You know, what's the precise definition? Not everyone agrees on what the formulation of it is. So that's why I tend to just kind of like stay away from it a little bit. But yeah, I mean, Jim has this experiment set up that he thought would work due to the Mach effect, and they're at least measuring something in the laboratory. So it's curious when that happens, right? You know, there has to be some explanation for what's causing this thing to move. So it's the place to start, I guess.
so Jim kind of said as an aside yesterday, we're producing newtons of force with watts of input. We're taking the energy from the universe. And for me, that made me pause, and I was like, wow, that's a lot more like than I had thought. And one of the things that I've felt for a long time, and I think a lot of people have seen this, is like your team has been doing meticulous work, right? It's very meticulous, it's very painstaking, but like the output thrust is very small. And I think that's easy for people to just get distracted, right? And not realize how much potential there is.
Yeah, that's, by the way, that's the peak thrust that Jim was referring to. So the average thrust is in the hundreds of millinewtons, and that's in the vacuum. So yeah, that's what we're seeing now with the way that we're doing the experiment. And so yeah, the work now is actually getting it the same effect and the same thrust with different variations of the experiment, because right now we're on a specific type of what's called a torsion balance, and you know, it could be that there's a nonlinear mechanical effect that we're seeing. So what I'd like to do is do the experiment on a different type of setup with the same thruster and show that, okay, it's not unique to that. So, and also we want replication, other labs to do this. So we're setting the devices up so that, you know, it could be sent out. And in addition, we have something called a Null test, where we can swap out the reaction masses and put equal reaction masses so the Mach effect goes away.
Okay.
Right. And I do want to say, in terms of the Mach principle, there's the Mach principle, which is, you know, Ernst Mach talked about the idea of Newton's bucket, right? So Newton had the idea of, okay, you take a bucket, you spin it, the water cusps. Like, why does that happen? So you can think of, okay, you're in space, you're spinning a bucket, what's it spinning relative to, right? There's no Earth. You look around, there's the distant stars. And so that's the idea, that the inertia of that water has to come from somehow with that distant stars.
So I didn't realize it was called Newton's bucket, but for me, I've had a very similar thought experiment. It was the rotating space station, right, where you stick to the walls through inertia.
Yeah.
And you know, and that's typically, I think that's constrained. It's described as constrained linear momentum, right? And the thing that I'd wondered about was, I said, okay, if you imagine you're, you know, next to the Earth and spinning, you could see the Earth spinning by. It's easy to understand that you're rotating, but kind of similar to what you were saying, if you take that out into deep space and you rotate it, I mean, maybe you can't even see the stars, right? So how do you know that you're rotating, but you'll still stick to the walls, right?
Yep. And so there's different ways of looking at that. And if you want like to go in depth, I would recommend Andre Aziz. He has some videos and works where he, you know, he has his own kind of formulation. It's not necessarily, there's like Newton's idea, Mach's idea, and then the idea he's developed. But but fundamentally, that's kind of Jim's point, is that Einstein was trying to incorporate that idea of inertial mass coming from that coupling with gravity to the distant stars or to something else.
Okay.
Whether it's the ether or what the actual specific mechanism, that's a step beyond where Jim is he's kind of drawn a line, said, okay, I'm just taking that at face value and then doing the derivation where he takes the four divergence and does his mathematical steps and out comes his the terms that he is depending on for this effect. And so it's kind of one of the analogies for lay people that I think as they were doing the NSF grant, they would give talks and stuff, is kind of like if you're on the ocean or on the sea and you're taking water buckets, you're heavier, you're pushing one way, you empty it, you push the other way, and then that way you're kind of like the sea would be analogous to the gravitational potential. So that's kind of at a late term you could think of it. All that being said, it's a tricky phenomena to get because it needs to have certain things happening where you're getting the right acceleration, you're having a change in energy happening at the same time, and so it's an effect that you have to have exactly the right phenomena happening, and you can dampen it out. So very easily it can go away if it's there, right? So it is a tricky thing experimentally too.
It is, and again, going back to the right now the output thrust or force levels are very low, but like you've mentioned over the last couple of days, like for instance, that peak thrust in newtons, I think Jim had described someone building tracking software. So instead of sweeping through a resonance range to try and capture that, you're actually able to hopefully lock onto it, right? Hit that more times per
Yeah.
And then you had also talked about just simply using smaller, thinner piezoelectric thrusters
Right.
allows you to create something like 10 times more thrust, right?
Yeah, in the theory, the amount of power that we're putting in and that change in power, the dPdt, is actually there's a power term to that, whether it's to the third or the sixth. There's different derivations that have been done, but if we have thinner disks, we're able to have higher power density, and that's that internal energy that Jim was mentioning. So we would have, in theory, 8 to 10 times more force, if the theory is correct, with those thinner disks as we change the power. So the thing is, it's tricky because if we change the disk, that changes the electrical resonance, and it could change the mechanical resonance, and so we would have to change. Right now, everything's tuned together.
Yeah.
So that the masses, because they are vibrating pretty violently, and when you have a piezoelectric material, as when you put forces on it, you are actually putting in electrical energy. So we're putting electrical energy into it with the voltage and the change in voltage, and as that piezoelectric material gets pushed back on, it's creating a voltage. So then you have a kind of a resonance, or you have a feedback to the electrical circuit. So all that needs to be tuned, and it's very, very, it's tricky to do. There's a lot of trial and error that's gone into the configuration we have now. So when we make that one change, that may set us back, and it may take time to get that change to work, right?
Well, that actually takes me exactly into something that Drew Arigma, over in the Florida lab, had said at Exodus Technologies. He'd said that someone very wise told him years ago, only change one thing per
Right.
test.
Yeah.
And he said it's tempting, right? You have a bunch of brainstorms, but he's like, I only make that one change because then if something happens, you won't know what's responsible for it.
That's right. Yeah. That's a very important way to go about things. So, yeah, and we, working with Jim, things, as you said earlier, things take time. So he likes to do things step by step. So right now, one of the issues is with supports. We were having issues before with the ball bearings on the steel rods, and it wasn't a repeatable test, because what would happen is, as the thing's vibrating violently, eventually those ball bearings would scorch and kind of make tracks in the rods. So Jim would have to like redo a whole setup, and it would kind of we'd get great results, and then after like a week or so, it was no longer repeatable. So when we send stuff out, who knows what they got. So us going to a composite bearing with the right materials that made it so that it's repeatable. But I mean, it's a very simple bearing. So there are mechanical effects that happen with it. Like sometimes we do see stick slip type reactions, where depending on the frequencies, you could have the mass going opposite ways. So that's a conventional type of thing, and that's not what we're looking for. We're looking for us, getting that Mach effect going. So
okay.
what we're it's a really hard engineering problem, because you have to let it vibrate freely, and at the same time have some way of transferring the force, and kind of constraining the motion to that linear motion.
Yeah.
So it's not an easy thing to do, because like Jim was saying, you put anything on, you attach anything that dampens the vibration, it has a negative impact on the effect, because all those vibrations, all that sound energy that's going through the materials and splashing back, that's part of the resonance that builds up and adds to the effect.
Oh, okay. Well, I shouldn't neglect David. So David, I mean, now that you've been here and seen this, I know this is just kind of a very cursory overview that you've given it. I mean, what are your thoughts on the devices that they're building and the performance there? Did anything jump out at you as areas that it could move forward, or areas that it might be like creating errors or extra noise or anything along those lines?
Yeah, I mean, it's hard for me. I'm still trying to honestly like work through the mechanism for how they were actually able to think that they would have this effect. So, I mean, I saw the thing basically move in the lab. So, something is causing it to move, and there has to be some description of how it's occurring. So, it seems like they're measuring some effect, whether it's from noises from nonlinear effects of oscillation that are just hard to predict, or if it's actually coming from the Mach principle, and I'm not sure yet. So.
Yeah.
I have to think about more. So Curtis, maybe you could just describe the setup of the experiment. So you have a stack of piezoelectrics, and then you have two different metals on each side. One was aluminum and brass, right?
Right.
And so that's giving you this kind of asymmetry in mass.
Right.
And so then you're pulsing the piezoelectrics with high voltage, or voltage at least.
Yes.
How high is the voltage, by the way? Probably
When it gets to the stack, because there's a step-out transformer, and there's like from the function generator that's generating the driving signal, there's actually an amplifier that was behind where Jim was sitting, and then from that there's actually a step-up transformer that is tuned to resonate electromagnetically with the actual stacks. So it's tuned to be the right voltage. It kind of as the stacks compress and send back energy, it kind of causes those harmonics that we're seeing. So by the time the voltage gets there, to answer your question, it's about in the range of 100 volts.
Okay.
And yeah, that's what we're putting in.
And so why would someone expect it to have everything accelerate in one direction based on Mach's principle then? So that there was you're adding in energy or mass, you could think of it that way, energy into the system. You wanted to get this change in mass going, and then you also want to get these vibrations going, and then the vibrations since the masses on both sides are different, there's kind of asymmetries on how the accelerations of the two sides
That's right.
would go. But how does that, where does Mach's principle coming in for the effect?
Well, Mach's principle is part of the derivation of the Mach effect that Jim coined, and so that Mach effect depends on those masses being the asymmetry of the masses. If we put equal masses, we don't get the same acceleration. So we can take the same stack, put two masses that are the same on either side, and it basically, you get some vibration, you get some, some of the motion of the stick slip and stuff like that, but you don't get that push. You don't see that.
Well,
now, the other thing I'll say is that depending on the and we didn't cover this today, but depending on the frequencies and the direction of the frequencies in the interaction, that force could go in either direction. So sometimes it could go towards the brass mass, and sometimes the force could be towards the aluminum side. It just depends. And the reason the asymmetry, and this is one of the issues that I had with it, because I'm looking at the equation, but I don't see mass 1 and mass 2 in there, right? It's not, there's other papers that talk about it, but it's not well, in my opinion, well done explicitly to show you that. But so basically, the way to think of it is that, if, like, let's say you're heavy, like, let's say the piezo stack is heavier as it pushes both, right? So it's going to get a push back from either mass, and it's going to, right? Because the brass is going to push less, and the aluminum is going to go further, right? But then when it's pulling back, because it's important to have the right harmonic. So when it's pulling back, you're pulling back in a way where you're not going as far. So you end up with this time averaged basically change in momentum, going in one direction. So it has to be the resonance all have to line up, and everything has to line up so that you get that perfect system where things are changing just so that you're pushing out when you're heavier, pulling in when you're lighter, and at the same time as the masses are reacting. Basically, you get that vibration, and they're pushing in at the same time. So that's why even the brass reaction mass, the thickness of that is very important, because you get that, the basically sound wave, the compression wave that comes back, and it has to be timed. Okay. So if it's not timed correctly, that's why as we sweep through, you see nothing happens, and then all of a sudden all this stuff happens and goes away.
So is the Mach effect this idea that if you change the acceleration of an object, it changes the mass? That seems to be what...
At the same time, you're changing the internal energy. So it has to be all these things lining up that you're doing at the right time, so that you get that. You're basically taking advantage of that kind of. It's a what Jim calls it is a transient effect that is there, in his derivation.
So how would you like state what the Mach effect is? How would you describe that?
How would I describe it?
Yeah.
I'd say it's possible that it's a transient feature of inertia that if we're able to time things right and change internal energy of a system, that you could basically push back against the gravitational potential that is around you. So that's kind of at a kind of basic level the way I would describe it.
So the way I guess the way I'm seeing it is you want to make things accelerate so the internal energy changes, and then have everything timed and synchronized in such a way that basically these accelerations, when something could energy could go one way and then bounce back, but now that the internal energy has changed, it's going to have a different response.
Yes.
Such that you want to time everything so that when you sum everything up, you end up getting a momentum flow in one direction versus the other, basically.
Yeah, and it ends up pushing against the gravitational potential of the rest of the universe. So that's the the key assumption is that the Mach principle is valid, right? Now we talked about real effects that you can measure. There have been other experiments like the ones done in the 70s with neutron diffraction that show that that's a real, the Mach principle is a real thing. Now the actual mechanism of what inertia is, and that's deeper and not explained in this. It's not part of this. This is an experimental, just taking, okay, there's a Mach principle, and Einstein was trying to incorporate it, and that's kind of the level Jim has gone to with that.
Yeah, you don't exactly have to know all the whys.
Yeah, all the mechanism. So he's taking the gravitational potential as, okay, c squared. So there you go, and yeah, that's where that is. So.
And that's interesting. I didn't realize there were neutron diffraction experiments that have been done in the past.
Yeah, that was something I found out about back in December when I saw Carl Mead's talk last year, Kyoto Prize talk, and yeah, he went over those experiments. It was interesting because that kind of breathed new life, and Jim got excited about it as well because having an experiment like that's basically a quantum type experiment showing that basically what they did is they had this neutron diffraction experiment where they did it at different angles, and they used basically the Earth rotating to do the rotation. So you would see a difference in the time of day. So that's we know that matter knows where it is to the rest of the to the rest of the universe somehow. Now, whether that's done through, this gravitational potential, what is the gravitational potential? Is it really an ether or not? Is it really, we're some kind of potential that's like waving out to the rest of the universe, gravity waves in some way? That's TBD, right?
Yeah, well, and that comes back to the very experimental nature of your work, right?
Yeah.
And that's one of the reasons I'm so excited to have David here, though, is the more people with theoretical backgrounds that are able to look at this, the more that, I think it helps to inform theory, but then the more theory may be able to be applied to it. But that being said, the work that you guys are doing is intentionally focused on experiment and not theory, right?
Yep. Especially with Jim, it's one of those things where we need to get a replication, that's important. That's been tried in the past. Things haven't always worked out. Like I said, it's with this, everything has to be lined up correctly. And in the past, they've tried different things, and allowed basically made changes over the years to allow the effect to come out easier. But at the same time, the having it repeatable is really hard to do because of what you're trying to do is really hard to engineer. So yeah, we still have a ways to go.
So you tested a new one today that Jim has lovingly called Big Ears.
Yeah.
And it has basically it has what looks like ears that are holding the bearings, right?
Right.
What are some of the upcoming tests that you're doing with this?
So what we have now is we have the aluminum cap and the brass reaction mass each have 3 ears, what Jim calls ears. So they're basically 3 supports where we have bearings. And currently, because we have simple sleeve bearings, so they're just like a cylinder that's in there, and they're composite and with steel rods. So currently, of the 6 supports points, Jim only puts bearings on 4 of them.
Okay.
Because what happens is those are simple bearings, and if they're not lined up correctly, those rods, you can get binding issues. So to me, this is an engineering problem, and the problem with having only one rod with bearings on that rod is that if you get any kind of motions that are not on the plane of or the direction that you want along that rod, you can get binding of those bearings as well. So the two other bearings that are on one of the on the brass mass is not enough. It should really have 6. Now I was hoping when we built this that he would put the 6 bearings there, but one change at a time, like you mentioned earlier. Jim wants to do the test with 4 bearings.
Okay.
So that's what he wants to do first. Now the other thing is it's difficult to build those devices. So if you put the 6 bearings, it would be even harder because you got to get it lined up. I don't know if you saw him building it, but it's tricky to build those little things. And so anyway, so ideally, you know, and by the way, so we have been using some lubricant, and he didn't use that in this test because we didn't want to see if it even needs it, right? So that was today. So he's going to add lubricant and see if that works and causes it to pass the jiggle test. And I was showing you guys earlier, if you jiggle it, it should freely move. That one wasn't really passing it because it was kind of binding. So those new bearings, they have the ability to self-align, and because of that, we should be able to use six points. So
okay.
what happens with a bearing on a rod is that, like, let's say you had a bearing and rods, and you had a device where, you know, you were moving it along. If you put force on it, like from a lever arm further away, you're actually torquing that device, and so that can cause binding where the bearings are not. You know, they're not just riding on it, they're having these lateral forces. So because he doesn't have all 6 bearings, it has motion, that's part of the reasons why we're getting some stick slip and other things happening. And also those support points, or what Jim calls ears, as this thing when we turn it on, these things are vibrating a lot. So even the bearings that are in there now, or the bigger bearings, don't have, they're not engineered for that kind of vibration. They will help, but the proper bearing that can withstand vibration and not transfer vibration, and also self-load, those are even larger. So after we test these, and if they work, we might go to have, you know, it's taking time, so I'm trying to get them to, let's put the right engineered bearings, let's have a system where it's like engineered correctly. But like I said, you make changes and it's such a subtle effect, you know, Jim is cautious of, okay, you're losing the effect if you make too many changes.
Yeah.
So it's really slow going because of that.
Yeah. Absolutely. Well, David, did you have anything else for right now?
Nothing coming to mind right now. Let's see.
Well, let me thank both of you. Thank you so much. I mean, Curtis, thank you for helping me understand and for, you know, giving me the tour of the lab and for working with Jim, everything that you are doing and have been doing. And you are just, I mean, I know that both of you are moving mountains. And David, thank you for coming out and spending time to learn about this and see it firsthand. It was absolutely wonderful to have you.
Definitely. Thanks for inviting us.
Yeah, thank you.